Hi guys, welcome to the first lectures on quantum field theory, and this is chapter 1, introduction. And the books we're going to use, or you may refer to, is Quantum Field Theory by Michio Kaku, Quantum Field Theory by Mundell and G. Shaw, Relativistic Quantum Mechanics and Field Theory by F. Gross. So quantum field theory, or QFT, is a framework that combines quantum mechanics and special relativity. It describes the behavior of small systems like atoms and particles moving at very high speeds, that is near the speed of light. Here we will exclude gravity. Recall the three ideas from quantum mechanics. First one is that all physical observables are mathematical operators in the theory. That is, they're in the form of derivatives or matrices or whatever. They're operators. They're not quantities, but they give out quantities when operated to a system. For example, the Hamiltonian, or the energy operator of a simple harmonic oscillator, looks like this one here. You have h, which is equal to h bar, which is Max Planck's constant, or Planck's constant, and then you have the frequency omega, and then you have there the creation operator multiplied to an annihilation operator. This means that when you operate it in a system, you have to operate with the annihilation operator first, then the creation operator, plus 1/2. By the way, your annihilation operator would just be equal to 1 over square root of 2m. M here acts as the mass of the particle, and then you have the quantity h bar over I dx, derivative with respect to x or space, minus I m omega x. So the adjoint would just be the complex conjugate of that. The second one is that the uncertainty principle must be observed. So in this equation that you can see, 1.1, you have the uncertainty or standard deviation. Actually, it's a standard deviation of the position and standard deviation of the momentum. The product is always greater than or equal to h bar over 2. And this means that when you measure x exactly, then you will not be able to measure the momentum exactly. Or if you want to measure the momentum carefully, then you have to sacrifice the measurement of the sacrifice the correct measurement of the position. It's the same with the energy and time. So if you have a system that gives off large energy, it happens in a very quick amount of time. Or if you have a system that evolves with time, then in a large amount of time, then you have the energy involved there is um, not so much. So these are what we have learned before. Remember that the uncertainty relation between energy and time is only a parameter in non-relativistic quantum mechanics and not an operator. The third one is the commutation relation. Like in this example, you have position and momentum. This one here. So there's a commutation relation between them. This means that if you write this, you have to write the difference between the product of the first and the second minus the product of the second and the first, and that is just IH bar. We've learned that in quantum mechanics. And for special relativity, the Einstein's famous equation, we must remember, is E is equal to mc squared. This asserts that if there's enough energy, which is proportional to the mass of the particle, then the particle or particles can be created. And conservation laws states that twice the particle's mass is needed so that a particle and its antiparticle are created. In high energy processes, you don't expect the number of particles to be constant from time to time, because many of these particles annihilate or many of these particles are also created, so it's never fixed. And this is in conflict with the non-relativistic quantum mechanics, because like in the Schrödinger equation here, this can be extended to treat the case when several particles are present. However, the number of and types of particles should be fixed. So we need an extensive theory that deals with particles of particle numbers that are not fixed. The Schrödinger equation cannot handle changing particle numbers or new types of particles appearing and disappearing as relativity allows. There's no wave equation in non-relativistic quantum mechanics that is absolutely compatible with both relativity and quantum theory. The first attempt to incorporate quantum mechanics and relativity is the Klein-Gordon equation. This one here. This will be discussed thoroughly later on. Here you have the speed of light, c, and the phi here is just the field. By the way, field can be represented by particles, or particles have fields. And this is just the second order derivative with respect to time, and then you have you subtract there the second order derivative of the field with respect to space, and then you have here the mass m of the particle representing the field, and of course the speed of light, the Planck's constant, and the field. It has an unwanted feature that appears to give negative probabilities, which is obviously contradictory to the concepts of quantum mechanics. And this also allows negative energy states. The next attempt was the Dirac equation here, where again your psi here are the fields, and the m is the mass of the particle, and the alpha and the betas here are matrices. In fact, they are 4 by 4 matrices, and the psi are actually 1 by 4 column matrix. So this equation resolves the problems of the Klein-Gordon equation, and this also allows negative energy. So more of these will be discussed later on in the following chapters. So in order to be compatible with special relativity, you treat phi and psi in the Klein-Gordon equation, Dirac equation, to be fields and not wave functions describing just a single particles. So they describe a lot of particles, not just one particle. And fields are operators that can create new particles and destroy also some particles. Field satisfies commutation relations between being themselves operators. So we now transition from quantum mechanics to quantum field theory, and here in this particular scenario you have position and momentum. This will be translated in quantum field theory in the form of field, and for the momentum you have another field called pi. And the commutation relation, as you can remember, x p, this is just equal to I h bar, and here you have I h bar times a Dirac Kronecker delta, where the arguments of x and y here should be falling into the same point to get IH bar. Unless they fall into the same point, you get 0. So this means that if two fields are spatially separated, they cannot affect one another. Note that in quantum mechanics, the position x is an operator while time t is just a parameter. In relativity, time and position are on similar footing and both are treated as parameters. So in quantum field theory, your fields are operators parameterized by space-time points xt, or should I say xt here. Position and time are just numbers, not operators, and momentum continues to play as an operator. In quantum field theory, some tools in classical mechanics are used to deal with fields like the Lagrangian. However, we'll be dealing with Lagrangian density in quantum field theory, but well, it means the same thing. So Lagrangian here is just the difference between kinetic and potential energy of a system. And we also use the classical path taken by a particle, which is S here, the integral of the Lagrangian. And of course, we will deal with paths that are minimized, or of which the action is minimized. S here is called the action. In special relativity, QFT operates in the high energy domain of this field, of this area. And this area is based on two simple postulates: that the laws of physics are the same for all inertial observers. By the way, an inertial frame is one that which Newton's first law holds. And the second one is the speed of light is a constant in any inertial frame. In special relativity also, a space-time is characterized by an event, something that happens at a particular time at some spatial location, XYZ in general. The speed of light serves as conversion factor, transforming time into space or space into time. Space-time, or space and time, form a unified framework and is denoted by the coordinates ct, xyz. One of the consequences of the second postulate is the invariance of the interval. So whenever this interval is measured in one inertial frame, that's the same measurement in other inertial frames. In special relativity, distance is measured in space and time together. Not only space, but you have to include the time here. So if you imagine a flash of light emitted at the origin at t is equal to 0, at a later time t, the spherical wavefront of light can be described by this one here, or that one. C squared t squared minus x squared minus y squared minus z squared should be 0. The speed of light is invariant, meaning it's a constant. The equation must also hold for another observer in another inertial frame. So here, this is also true. And therefore, this whole thing here should be equal to this thing. In ordinary space, the differential distance from one origin to some point xyz is given by this one. An analogous concept in space-time or in relativity, we call that an interval, and that is denoted or defined by this one here. So you have 4 components of an interval. So it follows from this equation that the interval is an invariant, meaning is that it does not change. Two observers in two different inertial frames measure different spatial coordinates, of course, that is x, y, z, and the other one should be x prime, x, y, y prime, and z prime. And they will also measure two different events. I mean, two the same. I mean, the event. I'm sorry. They will measure the event also at different times because they are in different inertial frames. So this one and this one. The interval for each observer is the same since the speed of light is the same for all inertial observers. So you have here this one. It doesn't mean that this one is the same as this one or this one is the same as this one. They're not the same. Only that the whole quantity is the same. An object called the metric can be used to write down the coefficients of the differentials in the interval. In this case, for a flat space, there are just 1 and negative ones. The metric of special relativity in flat space is eta mu nu with inverse of eta mu nu, but this time it is in the subscript. So here you have 1, negative 1, negative 1, negative 1 in the diagonal, and the rest are 0. This one also is the same. In this case, your eta mu nu is equal to eta mu nu. In general, you don't have all ones there. If you have a different space, not a flat space, then it wouldn't look like this. This is only for flat space or Minkowski space. Minkowski space. In general, you don't have a flat space, and in general also, the metric is denoted by G mu nu, and it has a property that if you multiply this one to this one, this is like covariant versions of the two metric, or just the inverse. The product is a Kronecker delta. And this is just 1 if mu is equal to rho and 0 if they're not. And of course, the inverse of the inverse times the original one is always an identity matrix. It is convenient to label coordinates by a number called an index. So these are here indices also, what you call an index, a lower index and an upper index. So CT can be labeled by x0, and your xyz would be x1, x2, and x3 respectively. And so an event in space-time is labeled by the coordinates of a contravariant vector. This one is a contravariant when the index is in the, if it is an upper index, that's a contravariant vector, and if it's a lower index, you have a covariant vector. This is also very important, contravariant and covariant. So your mu runs from 0, 1, 2, 3. So 0 is always for the time coordinate, and 1, 2, 3 are for the space coordinate. So an index can be raised or lowered using a metric. In this case, you have x alpha is equal to g alpha beta x beta. This is covariant. You have, this is covariant, and this one is a contravariant. You can make a coordinate to be a contravariant or a covariant by multiplying with a metric. So in this case, you have x beta, and then you're multiplying with a metric alpha beta. So here you just cancel the beta, and it will just give you an x alpha. So, and the other way around, when you want to make the index or make the quantity contravariant, then you can just multiply the contravariant metric with the covariant quantity, and this will just give you x alpha. Using the flat space or Minkowski space or Minkowski metric, your x0 is just, the contravariant, the covariant x0 and the contravariant x0 are just equal, and for the space you have one to be just the negative of the other. By the way, if you see this kind of expression, that's what you call Einstein Summation. So when an index is repeated in an expression once in a lowered position and once in a raised position, this indicates a sum. That is, this one here is just equal to this, or by shorthand, this is just that one. So in other words, your XA here, this one here, has a long version, which is just the sum of four terms. So you have here a beta appearing once, and in the lower part and in the upper part once. That means you have to sum. So this is just that. Be careful with that. It's a sum. Always a sum in when you see that in quantum field theory books. Now, Lorentz transformation connects or transforms an event from one inertial frame to another inertial frame. By the way, Lorentz transformation is denoted by lambda. And so if you consider an inertial frame or an event in an inertial frame, x prime mu moving along the x-axis, for example, with respect to another inertial frame, x mu with speed less than the speed of light. So this frame, in this frame, a particle may be moving in the x-axis, but in this frame it may not be moving in just one axis, but it could also be three axes. So your inertial frame or your frame of reference may be different from another frame of reference. That's why when you have the interval, it is measured with the same magnitude in different inertial frames. So the Lorentz transformation that connects the two frames is given by this. And this only changes the lambda, the beta, depending on the velocity of the system. And your gamma is just this one, the relativistic factor. So your beta is just equal to v over the speed of light. This is just the ratio of your event's speed over the speed of light. And then this one, gamma, is just 1 over square root of 1 minus beta square. So it is just specifically this one, or this is the compact version of this one. These are just the same. And then we also have rapidity phi, and the hyperbolic tangent of the phi is defined as the beta here. That's just, of course, the velocity over, the speed of the particle, or the speed of the event, divided by the speed of light. Using the rapidity, mathematically speaking, the Lorentz transformation can be viewed as a kind of rotation that rotates time and spatial coordinates into each other. That is, you have this one, and this one. This is how you calculate the velocity in one inertial frame to another inertial frame. And this is referred to as a boost. Now we go to the index notation, shorthand index notation for coordinates used in derivatives. So for the partial derivative with respect to time, this is just this one. And as you can see here, it's partial with respect to time, it's partial with respect to x, 0, which is a contravariant, and this one you have a covariant. And this one as well for the space. So don't be fooled by this one. This is contravariant derivative, but you're getting a partial differential with respect to a contravariant. This is a covariant derivative, and you're taking a partial derivative with respect to a contravariant. Well, that will result to a covariant derivative. So, raising the index, you can again use the metric to do that. And so in this case, these are just equal, and these are just the negative of one another. So this is for space, and this is time. So by the way, your mu, this is just partial with respect to x nu. Also in special relativity, you have what we call four vectors, because all physical vectors have spatial and time components. And you have here the vector written this way. This is the contravariant, and this one is the equivalent covariant, or you can write it like that way, meaning your ordinary vector, what you have learned in basic physics, is just a component of the four vector. You have the four momentum, and of course you have four current density or current. So four momentum has a component, has a time component and a space component. The magnitude of a vector is a scalar product and is computed using the generalized dot product. And this is just this one. This is, you can also write this as a square. And this is of course a dot a, the sum of four terms. So when you see two indices appearing once in the upper position and in once in the lower position, that's a sum. And of course you can write this as this one. This is also, you can write this as a nu also. So this invariant quantity is under Lorentz transformation. So it's the same in any inertial frame. A consequence of the invariant scalar product is this one. And your product of your two Lorentz matrix or Lorentz transformation is just the Kronecker delta. This means that this is equal to 1 when beta is equal to mu, and 0 if beta is not equal to mu. So when you get the derivative of a field phi, this one is written this way as as you can see, this one is just this one here. The derivative is a covariant 4 vector. The components of the vector are this one. It has 4 the contravariant 4 vector would be this one here. Contravariant derivative. For any 4 vector, the scalar product is computed using the four-dimensional generalization of the Laplacian called the D'Alembert operator. And this is just that. Yes, this one. It's not that. I mean, that's wrong. This is just this square. The magnitude of the energy momentum for vector gives the Einstein relation connecting energy, momentum, and mass. You can actually write this also as, if you set C is equal to 1, this is just P plus M square. Choosing a Lorentz transformation to boost a frame in which the free momentum of a particle is zero gives the famous relation of Einstein, which is just E equal to mc squared, the rest energy of the particles. Another important four vector is the conserved four current vector, and the components of this vector is the charge density rho, and the other three component is just the current density J. So this is the for current, and this one is the current density. And of course this is conserved, so it's constant. So whenever you get the derivative with respect to time and space is just equal to 0. This one. So now we're going to introduce particle physics very shortly. By the way, quantum field theory is very essential in particle physics. It describes the fundamental particles and their interactions in the standard model framework. And as far as experimental data is concerned, as well as the theoretical calculations, standard model is able to describe all physical phenomena except that of the interactions due to gravity. There are three fundamental interactions or forces described in the standard model, and these are the electromagnetic interaction, which is a combination of electric and magnetic forces, weak interaction, and strong interaction. Each force is mediated by a force-carrying particle called gauge boson, which has integer spin. By the way, electromagnetic interaction is mediated by photon, massless version of the mediating particles of the weak interactions, are W and Z. These are massive. And for the strong interactions, you have the gluons. There are 8 gluons. Each force is it's a The gauge bosons for the electromagnetic weak and strong forces are all spin 1 particles. If gravity is quantized, the force-carrying particle graviton is a spin 2 particle. Forces in nature are believed to come from the exchange of gauge bosons. There is a field or fields in each interaction, and the gauge bosons are its quanta. So that's why we study the field theory in order to describe these particles. The number of gauge bosons that exist in a particular field is given by the number of the generators of the field. And we will study this in the following chapters. For a particular field, the generators come from the unitary group used to describe the symmetries of the field. Again, this will be tackled more in the next chapters. So we start describing each of the forces. So the electromagnetic force, the symmetry group for the electromagnetic field is the unitary transformation U1. There is a single generator here, so there's one mediating particle called the photon, and it's massless. For now, it's massless for now. If photons would have mass, then this thing then the mass, this number should fall within the mass range of the photon. So anyway, the theory says it has no mass. Since the photon has spin 1, it has only two polarizations, 1 and -1. By the way, photons do not carry charge, it's neutral. Then we go to the weak force, which will be discussed later on more extensively and intensively as well. The gauge group of the weak force is SU2, which has 3 generators. So there are 3 physical gauge bosons that mediate the weak force, and these are the charge W boson and the neutral Z boson. These particles are superpositions of the generators of the group. The gauge bosons for the weak force are massive. Like W's have around 80 GeV and the Z has around 91 GeV as mass. By the way, the W bosons has charge of 1 and -1. So the massive gauge bosons of the weak interaction are spin 1 and can have 3 polarization states. The 3 polarization states is a consequence of being massive. Photon is a massless particle and it has only 2 polarizations. The strong force has a gauge group of SU3, which is, it has 8 generators represented by the Gell-Mann matrices. Gluons are the gauge bosons that corresponds to the generators. Gluons mediate interactions between quarks and are responsible for binding neutrons and protons together in the nucleus. And it is massless, but of course recent articles calculate the mass of the gluon. And again, being massless, it has 2 polarization states like the photon. And yeah, recent articles have calculated the mass of the photon, I mean the gluon. They carry color and this is the charge of the strong force, and this the whole thing of strong force associated with strong force is described by quantum chromodynamics, QCD. Since gluons also carry color charge, they can also interact among themselves, and they can even form like 4 gluon state or a 3 gluon state. The range of a force can be estimated, so it depends primarily on the mass of the gauge boson that mediates the force. This can be also, of course, you have to use the uncertainty principle to estimate it, and the amount of energy required for the exchange of a force mediating particle is found using Einstein's relation for the rest mass, and this is just and of course the uncertainty principle here is always greater than h bar over 2. So so if you maximize the time, then you would be able to get delta t equals h bar over mc square. I mean, this is written here. So if you use the speed of light to set an upper bound to the velocity of the force carrying particle, then you would have delta x would just be c delta t, and then that would give you the range of force, h bar over mc. And if m goes to 0 here, delta x would be infinity. That's the explanation why photon interacts to infinity, the range of force of electromagnetic force. Of course, for the gluons, mass is also 0. But why is it that the gluons only stick together in a short distance? I mean, shorter than the radius of a proton or a neutron. So that's the question. And actually, gluons follow different properties, and we will be studying those things later on. The range of the weak force is highly constrained because the gauge bosons have large masses, and with the mass of W being this much, 80 GeV over c square, or 80 GeV when you set c equal to 1, for example, gives the range of delta x to be 10 to the negative 3 femtometers. So this is the reason why the weak force is only observed within nuclear distances. So the range of force does not apply to the massless gluons because the strong force is more complicated and it involves confinement and asymptotic freedom. which we will study later also if it comes along. The charge of the strong force are the color charges. Gluons carry color, and color charge has a strange property. It exerts a constant force that binds color carrying particles together. The stronger the pull, the tighter it feels. It's like a rubber band that when you pull the ends away from each other, you experience more and more force to do it. But when you don't pull it, I mean you relax it and then you don't exert a force, then they behave like free particles. So that limits the range of the strong force, and it's believed to be in the order of femtometer within the radius of the proton and neutron. As a result of confinement, gluons are involved in mediating interactions between quarks, and gluons are causes also to bind neutrons and protons, but there are other factors why the three quarks bind together. If you read the book of Griffiths, you can see some detailed explanations there. So for our next lecture, we will be starting with elementary particles. We will introduce what the elementary particles are, the kinds of particles that we have in the standard model, and so this ends the session for this meeting, and hopefully for the second one you will learn more about elementary particles. So that's it for today.